The upcoming chapter 15 is introduces and develops the topic of solutions, and this will be the only chapter covered in Exam 6. So let me share the PowerPoint, and that's not working. Hold on a second. Share. Here we go. There we go. And there's our set of PowerPoints. We're chapter 15. All right. Solutions are extremely important in chemistry. For one thing, there are a great many reactions that occur in solutions and are facilitated by solution chemistry. And that, for those of us who are active in the life sciences or are planning to be, solution chemistry is even more vital because all the reactions that occur in the human body, most of them in fact, are occur in solutions. Now, from a purely chemical standpoint, the stoichiometry that takes place in a chemical reaction is well characterized in solution, and the activity of the components is better controlled when we know the exact concentration of the reactants and products that come out of a chemical reaction. So we're going to study solutions today, and first we need to define what a solution is. This is essential because a solution is a homogeneous mixture, and as such, every part of a solution, no matter where you sample the solution, the composition of the solution is the same. Any homogeneous mixture is that way by definition. That way you can take any small part of a larger solution and expect to find the same percentage of each component in that sample. Okay, so a solution is made up of two parts: the solvent, which is the major component, and a solute, which is the lesser amount. All right, there's one. Okay. So when you, for instance, when you prepare a solution of salt water, you have a very large amount of water and you add just a small amount of salt to it. The salt is the solute and the water is the solvent. Another characteristic of solutions that is important is that there can only be one solvent, but there can be many solutes. You could mix up, I don't know who would want to, but you could mix up a solution with water as the solvent and sugar, and salt, and lemon juice, various components that would be considered solutes. Now, there are cases where the solute concentration, or the amount of solute in there, is greater than the solvent. For instance, preparation of solutions of sugar and water. For instance, when you prepare a a sugar solution for your bird feeder, your hummingbird feeder, you typically put equal amounts of sugar and water. But you could go even higher than that with the sugar, and it would still go into solution. It would produce a homogeneous mixture at extremely high concentrations of the sugar. But we still consider the sugar the solute because you generally start with a large amount of water and you add sugar to it gradually. So the beginning situation is that the sugar is the smaller amount and the water is the larger amount. And we hold that relationship even up to very high concentrations of sugar in water. The types of solutions that we're going to study in this chapter are aqueous solutions. That is, the solvent is water. And whenever we write them in a chemical reaction, we will follow, for instance, salt water. If we had sodium chloride in solution, we would follow it with AQ, which stands for aqueous. All right. So solutions are homogeneous mixtures. Now, there are various types of solutions. They don't all have to be aqueous, that is, water as the solvent. Any type of homogeneous mixture is considered a solution. So you could have multiple gases together forming a solution. And that's the case with our atmosphere. 79% of the atmosphere is nitrogen. So that would be the major component, and technically we would consider nitrogen as the solvent. And then minor, lesser components like oxygen at 20%, argon at about 1%, and then lesser amounts for the remaining gases. But one characteristic of gases in solution is when you put two or more gases together, they always form a solution every time, without exception. Primarily because there's plenty of room in there. There's lots of room between the molecules of gases. So there's no hindrance to their mixing. Other types of solution, you could have two liquids together to make a solution, and that's the case with all types of alcoholic beverages, or pop. That's not a good example because I'm going to use that for a different one. Antifreeze, for instance, in the engine of your car. In the radiator, you'll have ethylene glycol will be the solute, and water will be the solvent. Typically, the mixture is 50-50. That is, you'll have equal amount of water and antifreeze. But we consider the water as the solvent, and the ethylene glycol is the solute. Brass. Who would think that a solid could be a solution? But it is. It's a homogeneous mixture. Brass is predominantly copper as the solvent, and nickel is the solute. Now, you can't mix them as solids. I mean, you put them together like that, they won't go together. But you have to heat them up and melt them, mix them up, and then when they solidify, you have your solid solution. Pop, that I mentioned earlier, is better thought of as a solution of a liquid, water, and a gas. Solute is carbon dioxide. And then what we normally think of as a solution, a solid dissolved in a liquid, like seawater, is predominantly sodium chloride in water, but there are other components. There are calcium salts, there are magnesium salts, potassium salts mixed in there. It's a complex mixture with lots of solutes, but one solvent, water. So, what can we say about the how solutions are formed? They can be broken down into basically two forms of solution. One type is where the solute breaks apart when it goes into solution, and now we're going to focus on water as the solvent. Right, so we have water as the solvent, and then we could have solute ionic solid, such as sodium chloride. So when an ionic solid goes into solution, an aqueous solution, it breaks apart into individual ions. Okay? And those ions, because water is a polar solvent, that is, the water molecule has a positive and a negative side to it, right? Like this, right? H2O. This side is going to be slightly negative, and this side will be positive. Right? So because water is a polar solvent, it is strongly attracted to ions. Right? This negative end will be attracted to that positive ion. These positive ends will be attracted to that negative end, and that facilitates the dissolution of sodium chloride or any ionic solid in solution, as long as the ionic solid, in fact, does break apart into ions. There are some instances where the ionic solid, the bond between the ions is so strong that it will not break apart in aqueous solution. But sodium chloride is an example where you do get that formation of ions. The other type of solution forms from molecular solids. Right? For instance, sucrose or table sugar. When it goes into solution, it does not break apart. It's a whole molecule and stays a whole molecule while in solution. So what happens is a similar effect to the ionic solid dissolving is that the sucrose molecule has lots of these types of, we call them ligands, OH groups surrounding the sucrose molecule. Well, what that does is it makes this slightly negative and that slightly positive. And the water molecule then comes in with its negative side and associates with that positive here, or associates with the oxygen for its positive side, the hydrogens on the water molecule. So you get this dipole attraction that helps the solute go into solution. But those are the two basic forms. Either it stays a molecule or it breaks apart because it's an ionic solid. Okay. Let's see. I'm not seeing myself. I know this is being shared, and I see I see Natasha, but I don't see myself.
I can see you.
Okay. Is my board still completely on screen?
Yeah.
That's my concern. If I can't see the board on my monitor, then I don't know if it's walked itself off the video.
No, it's in the middle.
Okay, good. All right, so we have the ionic possibilities for dissolution, and then we have the molecular types. The ionics, of course, break into individual ions. And that's important later when we talk about concentration, how to calculate concentrations of solutions. And we have to be specific about whether we're talking about the whole formula unit, sodium chloride, for instance, or are we talking about ionic concentration, which is extremely important when you're planning on preparing a solution to be injected into a patient. And I'll explain why that's important later. I mentioned polar water molecules that interact with these ions. And this is an artist's rendition. What we call this is, the general term is called solvation, where the solvent molecules attack the structure of the ionic crystal, and they pull the ions away from the crystal, the solid. The specific term where water is a solvent, we call this hydration. And we get the individual ions are surrounded by water molecules. They're attracted, purely electrostatic attraction. Positive attracts negative. I mentioned the polar nature of the bond. There's a, let's see, have we talked about this yet? Periodic table. We've discussed the periodic table, but I don't think we've talked about the trends in the periodic table. No. Okay. Well, this is in an introductory course, so we don't get into that much detail. But there's this characteristic of elements called electronegativity. And it simply means that elements have a stronger or weaker attraction for electrons. So when you place an element or an atom in a bond with another atom, if they're not the same element, then you typically get an uneven distribution of electron density between the two. For instance, when we're talking about the water molecule, oxygen is more electronegative than hydrogen. So it tends to pull the electrons toward the oxygen. And we use this funny looking arrow with a plus sign on one end. That means that the positive end is toward this side and the negative is toward that side. And the reason we use this Greek letter delta, the small Greek letter delta, is to indicate that it's not a complete charge. In other words, we didn't transfer an electron completely from one side to the other. It's only a slight movement of electron density toward the negative side. If we were to draw an electron density map, it might look like so. We have more electron density up here, which make it more negative, but not completely negative charge. And then positive toward the hydrogens. what that does is it creates a polar nature of the bond and the molecule. And that's what allows water to be attracted to other, say the solute, attracted to a solute with a similar characteristic. If it's not a complete ion, then perhaps your solute, like this molecule here, which is ethanol, has the potential for an uneven distribution of electron density, which makes for slight negative and slight positive differential in that bond. So then the water molecule can be attracted negative side to positive side on the solute molecule. And what that does is it facilitates the dissolution of the solute into the solvent. So that's why they say, as a general rule, you may have heard this, like dissolves like. All that means is polar solvents tend to dissolve polar solutes, and nonpolar solvents tend to dissolve nonpolar solutes. For instance, water will dissolve polar solutes like sugar, salt, various other types, but it will not dissolve oil. Right? If you put, you can put vinegar or acetic acid in water and it goes into solution perfectly all right, because acetic acid forms ions, and it, in addition to that, it's polar on some parts of the molecule. But if you try to take that vinegar water and add oil to it, say you're trying to make your homemade salad dressing, vinegar and oil, they don't mix. You can shake them up and get some mixing, but if you let it sit, very quickly the oil will rise to the top and separate. The oil is a nonpolar solute, and the water is a polar solvent. They don't like each other, and this is the primary reason, because of that polar characteristic of water and the nonpolar characteristic of the oil. Now, water is often referred to as the universal solvent, which is kind of a stretch, simply because nonpolar solutes won't go into solution, not to any great extent. Be that as it may, ethanol, the drinking kind of alcohol, goes into solution readily, simply because of that polar nature to part of the molecule. Now, that being said, some molecules are large enough so that part of the molecule is polar and the other part of the molecule is nonpolar. A perfect example is soap. If your grandmother or father ever made soap and you watched how they made it, what they were doing was they were taking fat or lard and they were breaking it apart using lye, sodium hydroxide. And what that did was that converted the fat into a glycerin molecule plus the fatty acids. And the fatty acids are a very long chain, carbon chain, which is the nonpolar end. And then on one end of it, it has an acid unit to which you attach a sodium ion. So that's your polar side, and the nonpolar side is that long chain. That's why soaps clean the oils and dirt from your clothing, because they bridge the gap between polar and nonpolar. Most of the soiling that occurs in your clothing has oil in it. like from your skin or from whatever else, whatever other source. And to get that oil out and put it in aqueous solution so you can wash it away, you need something that will dissolve in the oil on one end of the molecule, and the other end of the molecule dissolves in water. It bridges the gap. And that's why the oil then will be removed from your clothing in aqueous solution. Okay. All right. So this is the structure of sucrose, table sugar. You don't have to memorize this. I mean, it's just illustrating the polar sites on the molecule. Wherever you have an OH, here and here, there, all over here, here, lots of them. Wherever you have those OH groups, you have a polar characteristic, a polar bond. Right? So you have this and that, and then attached to something else. So you will have the slightly negative side here and slightly positive there. And that allows water to be attracted to the molecule. There's so many of these sites all around the molecule. That's why sugar is extremely soluble. In fact, to very, very high concentrations. In fact, companies that use sucrose in their manufacturing process will receive delivery of sugar very often in liquid form. Because there's so little water in there, most of what is in the tank is sucrose. 90% sucrose, which is good because they don't need the water, they need the sucrose, but the liquid nature, the form of that solution is liquid, is easier to move around in the factory. You can pump it through pipes to different locations rather than having to handle the solid. And the only reason they can do that is because sucrose is extremely soluble. Okay, just a side note, the sucrose molecule is made up of two units. This unit down here, this one that looked, this 5-membered ring, is fructose. And this membered ring is glucose, the same sugar that circulates in your blood and provides energy to all your cells. Most sweeteners nowadays have lots more fructose in it than they do sucrose. If you break this molecule apart, it becomes sweeter. And there are physiological reasons for that. But you've heard of high fructose corn syrup. It's enriched in fructose. Fructose is a sweeter molecule than glucose or sucrose, either one. So they get more sweetening out of less product. Also, honey. Honey is naturally, the bees, when they gather nectar, they have an enzyme in their saliva that breaks the molecule apart and makes it sweeter. Plus, it, I'm going to use a term now that we haven't covered, it increases the osmotic pressure of the solution and helps preserve it. The higher the osmotic pressure, the more difficult it is for microbes to grow in it. So that's why you can set sugar out on your counter at room temperature for months, and it will not spoil. because the osmotic pressure of the honey is so high that there are no microorganisms that can grow in it. It completely dehydrates them. Okay, so I'm getting off topic now. So that's why these molecules, these molecular solids, are very soluble. See, there are no ions in here. It doesn't break apart into ions. It goes straight into solution as the entire molecule. Okay. Certain things I mentioned earlier are insoluble in water. So if you try to mix water and oil, you can form a temporary emulsion, we call it, where you can break apart the size of the particles of the oil small enough to where it looks like they're in solution, but they're not really. Okay, there I am. But I lost Natasha. Okay. There you are. Ah, and there I am. I found me. Okay. So, oil does not mix in water. It's not soluble in water simply because there are no polar bonds on the oil molecule. So when you have an oil tanker run aground and start spilling its contents into the sea, it generally forms a slick on the surface of the water because it will not mix with water. The only thing that will cause it to settle out is if the waves churn up sediment from the bottom, and then that attaches to the oil and then it settles out. But it does not dissolve in water. Salad dressing, if you mix it up, salad dressing, shake it up real good and pour it on your salad before it has a chance to separate. Okay. This bond, this arrangement here, is a special kind of polar bond which allows for something we call hydrogen bonding. Whenever you have hydrogen attached to oxygen or nitrogen, sometimes sulfur here instead of oxygen, then you get the chance to have that polar nature of the bond. And as long as hydrogen's involved, we have a very, very polar bond, which makes for a strong attraction to other molecules with polar bonds or with ions. Okay, how do solutes actually go into solution? What's involved in that process? Well, I've said it before, and I'll say it again. Nature just does what it does, right? And we try to break things up, break nature up into smaller pieces so that we can understand it. So that's what we're going to do here. When we talk about something going into solution, you have the solute and the solvent here. First thing you have to do is make a hole. So what that means is the solvent molecules are attracted to one another. And what you have to do is pull them apart. Make space so that you can put your solute into it. So that takes energy. You have to put energy into it. Right? You have to put energy in and break those solvent molecules apart. far enough so that you can put something in there. The solute, similarly, you have to input energy to break up the solute, because the solute molecules are attracted to one another, or ions are attracted to one another. You need to pull them apart. So that takes energy. So you have to put energy in here, you have to put energy in there. Then the solute goes into the hole and forms bonds of a certain type with the solvent. So it's 3 steps. Make a hole, break it apart, put them together. And usually in this step, you get energy back. Right? So you put energy in here, put energy in here, you get energy back there. Now, you'll notice that when you put something in solution, sometimes it gets cold. Other times it gets warm. That's the whole, that's the reason that hot packs and cold packs in the hospital setting work the way they do. Remember, they're just plastic bags and they have water in them, plus they have a little capsule of something inside. And what you do is you break it, right, and you mix that, whatever's in that capsule, in with the water. If it's a hot pack, the solution will get warm. If it's a cold pack, it'll get cold. And it all depends upon this scenario, right? If you put in energy, and you put in energy, right, you should feel cold. But if you get more energy back than you put in, it's going to get warm. If you get less energy back than you put in, it's going to get cold. Right? So that's the whole premise behind hot packs and cold packs in the medical setting. And of course, because of that, you can only use them once. Right? You form the solution once, that's it. There are reusable hot packs, but and it's based on this similar situation, but it's actually not a solution problem, it's a phase change problem. So they're really, they're similar, but they're not, if that makes any sense. Okay, so we got this 3-step process. We made a hole, and then when we put things together, that's where we get the water solute interaction. That's what this is. This is where you get these two coming together. You get we're using water here. Okay, so we'll be consistent with the slide. Water here, and this is just some other solute. So when you put them together, that's where you get this water solute interaction. Whereas we put energy in to the water-water interaction to break it apart. I don't think they mentioned, though, the other part. They don't mention this part where you actually have to put energy in to pull the solute molecules apart. And like dissolves like. And it all depends on this energy relationship. Okay, enough said about that. Okay, which of the following solutes will generally not dissolve in the specified solvent? All right, so let's say carbon tetrachloride mixed with water. All right, in order to decide whether a solution will form, and to use our rule of thumb, is to decide the polar relationship Water is a polar solvent, right? If we mix carbon tetrachloride in water, what should we expect? Well, you have to know something about the structure and the polarity of the solute molecule, right? So we know about water, it's polar. How about carbon tetrachloride? Carbon tetrachloride has a carbon in the middle, and then it has a chlorine here, and a chlorine there, and a chlorine there, and then behind it, there's another chlorine in the background. What we see is this is a regular, perfectly symmetrical structure. Now, the individual bonds are polar toward the chlorine. But they're all pulling at symmetrical points of a tetrahedron, right? A four-pointed, 1, 2, 3, 4, four-pointed regular structure. And what they do is they cancel one another out. So the whole molecule is nonpolar. Right? So a nonpolar molecule will not dissolve in a polar solvent. So this one is insoluble. Right? So that's one of them. How about ammonia mixed with water? Okay, we have to know something about the ammonia structure. Ammonia looks like this. Right? With this triangular base here on the bottom. Right, those hydrogens. And then there's a lone pair of electrons up there. That makes this molecule polar. Right? It goes polar for the bonds like this. Plus, you got this negative side to the molecule up here. It makes the entire molecule polar. All right, so that will go into solution. Methanol, right? The kind of alcohol you don't drink, wood alcohol, it'll make you go blind, has this OH unit on it. That's polar. So it is very readily dissolved in water. Nitrogen mixed with methane, right? These two gases, right? Methane is a gas, nitrogen is a gas. That's easy. All gases dissolve in one another, right? So the only one that's not soluble is carbon tetrachloride. Okay. Very often we generalize sometimes by saying soluble, insoluble, as if it's black and white. But in fact, it's on a continuum, right? If you say soluble out here and insoluble over here, there are various degrees of solubility in between. Right? So, when we say a solution is saturated, that means it holds at that given temperature, right? It's temperature dependent. At that given temperature, that solution will not receive any more solute. Is the maximum amount of solute that you can put in that solvent. That's a saturated solution. I'm trying to think of an example. Can't think of a good one. You can make a saturated solution of salt water, sodium chloride, and I've done it. You just you look it up, right? They're reference manuals that will give you an idea, give you actually an exact number. What's the solubility of salt in water at a given temperature? And it usually reads so many grams per 100 mils of solvent. So what does that mean? That's actually percent, parts per 100. But they're actually saying it's mass per volume. So it'll give you that number. So what you do is you heat up your solution, heat up the solvent, 10, 20 degrees hotter, is plenty. And then you take this many grams plus extra, say 10% more or 20% more. Put it in solution, dissolve it. And at a higher temperature, it generally, in most cases, will go into solution, all of it. And then you set it on your bench and let it cool down. And as it cools down, the solubility decreases as temperature decreases. And anything that's not soluble will drop out of solution as a solid. They'll form a layer on the bottom of the beaker. Now, the one thing you have to be careful with is as you cool it down, if it's undisturbed, what it may do is become supersaturated. So what you do is you just drop a small crystal. Once it cools down, you drop a small crystal of your solute in there, and that gives it something to gather around, and that will remove excess. And then once you've let it settle, the solution that you have left over is saturated at that temperature. All right. Anything less than saturated is unsaturated. It's just that simple terminology. Now, this supersaturated solution, some solutes tend to form supersaturated solutions easier than others. But most solutions can be coaxed into forming supersaturated solutions. The key is don't provide any place for the solid to accumulate. In other words, don't put any crystals in there of solid, right, so it can form around that solid. Don't have any scratches on the inside of your beaker. Right? That's one way to start a supersaturated solution to precipitate the solid, the excess solid, is to just take your spatula and scratch the inside of the beaker, and it'll start, the excess will start coming out of solution. All right, so you've got saturated, you've got unsaturated, and on occasion, supersaturated solutions. These solutions are very unstable. In other words, all you have to do is disturb them a little bit, and they'll lose that extra amount of solute. All right, we've said that before. Solutions are mixtures. They're homogeneous mixtures. And the amount of substance as solute that you can put into the solution varies up to the point of saturation. So anything below that can be variable. So what we need is a way to express that variability, that concentration of solute in the solvent. And there are various ways to do that. Some are useful in some situations, and you may have to use a different expression in another situation. But they always specify the amount of solvent that is dissolved in the total. Sometimes reference to the solvent, excuse me. Let me back up. They always specify the amount of solute dissolved in the solution, sometimes referenced to the total amount of solution, sometimes referenced to just the solvent. Okay. All right, before we get to the quantitative expression, there are some qualitative descriptions of concentration. Concentrated just means a relatively large amount of solute. So that sucrose solution in the big tanker that's being pumped around the factory, that is extremely high concentrated solution. We often use concentrated solutions in the laboratory. For instance, sulfuric acid can be obtained in a bottle, 98% sulfuric acid, extremely concentrated, and as a consequence, very dangerous. Nitric acid can be obtained at very high concentrations, but we generally stop at about 70%. What's the opposite of concentrated? Dilute. Relatively small amounts of solute are in solution. And we can use the quantitative expressions to describe these in more exact terms. One of those expressions is simply mass percent. Right? What's the mass of the solute relative to the mass of the whole solution? That is, solute, solvent, any other solutes that are in there, the total mass of the solution ratioed to the mass of the solute times 100. That's mass percent. So if you're doing this calculation, be sure that if you have to add everything up, then be sure and place the mass of the solute in the denominator also, because it's part of the solution. Right? So the mass of the solute, the mass of the solvent go in the denominator, and the mass of the solute goes in the numerator. So for instance, mass percent, if you have 5.5 grams of glucose and you place it in 78.2 grams of water, you just mix them together, then calculate the mass percent of glucose in solution. Right? You just say 5.5 grams in the numerator, 5.5 plus 78.2 in the denominator, times 100, and you have 6.6% glucose. Now, if you just see this term right here, 6.6%, there's no way to tell what it means, because percent is a dimensionless number. If you say percent, that simply means parts per 100. So what parts here and what parts there? That's why percent is a dangerous expression. We have to use it. It's a legacy, right? It came before chemistry. So very often we express percent like this, and we'll say mass, mass. That's what this would be, 6.6% mass, which means mass of the solute, mass of the solution. Another way of expressing concentration, which in many cases is more useful, is called molarity. And molarity is given this symbol, large M. If you have the capability of using italic large M, that's what this is. It eliminates confusion if you can do that. But it simply means the moles of solute per liter of solution. Okay, that's it. You need to know how many moles of solute you have and the final volume of the solution. Not the volume of the solvent, the volume of the solution. Okay, so also I'll point out that this is an equation. Molarity equals moles divided by volume in liters. So if you know two of these, you can solve for the other one. If you already know the molarity and you know the solution that you have, you can find out how many moles there are of your solute in that, what you have in your possession. Right? So it's like any other equation. If you have one unknown left over, you can solve for it. So here we find that 3 molar hydrochloric acid, in this case, is composed of 6 moles of HCl in 2 liters of solution. That gives you 3 molar hydrochloric acid. What about 1 mole of sugar in 125 milliliters of solution? Right? We have to go back to the definition. We got moles of sugar, right? There. Which is what? 1.00 mole. How many liters do we have? We have 125 milliliters. How many liters is that? You move the decimal place 3 places to the left, right? If the unit of measure, 25 milliliters, if the unit of measure gets bigger from milliliters to liters, then the number has to get smaller, right? So we go there. The unit gets bigger from here to here, milliliters to liters gets bigger, so the number has to get smaller. They're inverse. So that's the way I use to be sure that I'm not moving the decimal in the wrong direction. So we move it tens, hundreds, thousands. And that gives us 0.125 liters. Okay? Then you just pull out your calculator and take the reciprocal of 0.125. This does the conversion for you right there, right? You can use dimensional analysis. That's perfectly all right. You could take this, milliliters on the bottom, right? So they cancel. So that's 10 to the third, and liters on the top. Okay. And that'll give you 0.125 liters. You divide that into 1 mole, there, and you have a solution that's 8 molar in sucrose, table sugar. Let's see, let me check my time. Okay, we're good. All right. So what do you do if you're given a problem where you're given the mass of the solute and the volume? You've got to determine the number of moles of the solute in order to calculate the molarity. So in this word problem, if you don't know how to write the formula for potassium phosphate, then that's it. You're done. You can't go any further. That's why in the beginning I hammered learning how to write formulas from the names. If you can't do that, then it's all over. The game's over. You're stuck. You can't answer the question. So we got to be able to write potassium phosphate, because you've got to calculate the molar mass of the potassium phosphate formula in order to determine the number of moles. So we've got potassium, and we got phosphate, not phosphorus, phosphate. It's a polyatomic ion. So you look it up in your table, like that. But we're not done yet. Potassium is an alkali metal. It always has a +1 charge. Phosphate is always a 3- charge. Okay. So in order to balance the charges, you need 3 positives. There we go. Now you've got your formula. Now we can determine the molar mass for that compound. We need 3 times potassium. Potassium is 39.10. So we have 3 times 39.10. And this is grams per mole. Then we have 1 phosphorus, which is 30.97. And then we have 4 oxygens, 16 each. Right? So now we just need to pull out our calculator and determine the molar mass. Now, why am I doing that? Because we're given 500 grams of potassium phosphate. We're not told how many moles that is. We have to calculate it. So 39.1 times 3 is 117.3. And then we add that together with 30.97. And then we add that together with 16 times 4 is what? 64. So it's 212.27. grams per mole of that compound. Okay, so now we have to determine how many moles do we have if we have 500 grams. Let's see, that's an extra 0. 500 grams of our compound, and we're going to convert it to moles. So we need 212 on the bottom, right there, per mole. Okay, remember, conversion factors are equal to 1. So if you need to flip it, no problem. It's still equal to 1 either way. But we need it this way so the grams cancel and leave us with moles. So we say 500 divided by 212.27. We have 2.355. 2.355 moles. Okay? So now we can do the calculation. We know that we have 1.5 here liters of solution. So the molarity is going to be 2.355 moles per 1.5 liters. So let's see, we've got for 2 significant figures here, which means 1.6 molar. Round it off to 2 significant figures. All right, so, oh, no, I'm sorry. I'm cheating myself out of a significant figure. So rounded off, it's actually 2.57 molar. Okay? All right. Okay, so let's take another one, only this time we're not going to calculate the molarity. We're going to use molarity to find the volume. Let's say for this problem, you know you have a 10 molar sucrose solution. And you want to remove the correct volume of that solution that will guarantee that you have 2 moles of sugar in your possession. So if we look at the formula, and that's my abbreviation for moles, little n, and there's the volume. So we have 10 molar. Right there. And we need 2. And the volume is the unknown. Right? So all you have to do is solve for this one. Right? Volume comes over here, molarity comes over there, and volume then is equal to 2/10 or 1/5, which is what? 0.20 liters. Right? A fraction of a liter is unusual to find in laboratory glassware. It's usually in milliliters. So how many milliliters would that be? Well, remember, you're going from larger to smaller, so the number has to go from smaller to larger. So you move it 3 to the right. 1, 2, 3. 200 milliliters. Now the answer here might be in liters. Yeah, it's in liters. But we've got 3 significant figures. I should have put 3 here. It's 2 moles. There. So that means we can put a decimal there and preserve all these 3 significant figures. Okay. Let's try another one. Suppose we have 2 different solutions. One is sodium hydroxide, and the other is potassium chloride. And you make each one out of the same mass and the same final volume. What's your guess? Are they going to be equal molarity concentrations? It's unlikely, right? Why? Because with the same masses, you have different moles, because the molar mass of sodium hydroxide is not the same as the molar mass of potassium chloride. So they should have different values for their molarities. In order to do the calculation, first of all, we need to know how many moles of each one that you have. So if you have 100 grams of sodium hydroxide and 100 grams of potassium chloride, we need to convert those to moles, right? So you need a number here that cancels grams and leaves moles. So remember, whenever you have mass and moles in a quotient like that, it's always molar mass. So what's the molar mass of sodium hydroxide? Well, let's see. Sodium is 22.99. Oxygen is 16. Hydrogen is 1.01. So that's exactly 40. Okay. While I've got it in my calculator, I'll go ahead and calculate 100 grams divided by that number. 2.5. Three significant figures. 2.50 moles. Okay. How about potassium chloride? Well, potassium is 39.10. And chlorine is 35.45. So that's 74.55. Divide that into 100. 1.34. Yeah, 1.34. There we go. Now we can calculate molarity, but what's the volume? The volume is in milliliters. So how many liters is that? All right, we're going from milliliters to liters, from small to big. So the number has to go from big to small. So 3 places to the left gives you 0.2500 liters. Like that. And that's probably 10 molar. Yeah, 10 molar, 3 places, 10.0 molar. This one is 1.34 moles divided by 0.25 liters. 1.34 divided by 0.25, 5.36. Molar. Okay? So we were right. They are different molar concentrations. Might be the same mass. And in fact, if we calculated the mass percent for each of these, they would be identical, because it's the same mass per the total. And the total is the same. All right, so the mass percent can be equal, but the molarity is different. All right, rounding error. So that 5.37, I got 5.36. Okay. So let me clear off my board here. All right. Sure it stays on screen. All right. Suppose you have 2 hydrochloric acid solutions. Solution A, solution B. Solution A has a greater concentration than solution B. Which of the following statements is true? So A is more concentrated than B. Let's put that up here. Let's say, since we're talking about molarity, let's just say the molarity of A is greater than the molarity of B. And that would make sense because they're both hydrochloric acid. All right. A, if you have equal volumes of both solutions, solution B must contain more moles of hydrochloric acid. That can't be true. If you have equal volumes, that means A has to have more moles in the same volume as B to be more concentrated. That's the definition, right? So if this is greater and this is the same for both of them, then the only way they can get there is if the moles is greater for A. So A is false. How about B? If you have equal moles of HCl in both solutions, solution B must have a greater volume. Okay, equal moles in each one. But this one has to be bigger for A. So how does it get there? It gets there by smaller V, smaller volume. So the volume of A would be smaller than B. Is that what it's saying? Yes, solution B must have a greater volume. B is true. Okay, how about C? To obtain equal concentrations of both solutions, you must add a certain amount of water to solution B. If you add more volume to B, that makes it more dilute, which decreases its concentration. So C has to be false. How about D? Add more moles of HCl to both solutions will make them less concentrated. If you add more moles of HCl to either one, it makes it more concentrated. Both of them. So that's false. B is the only true one in that bunch. All right. Now, we know how to determine the concentration of the formula unit, or the molecules, the molecular concentration. What does that have to do with the concentration of ions? It only has something to do with the ion concentration if the compound is ionic. If it's molecular, it's a non-issue because it does not break apart. Pardon me. Okay. So let's look at an ionic compound in solution, calcium chloride, which is completely soluble. I mean, that's given, of course. And the concentration of calcium chloride is 0.25 molar. Aqueous solution. All right. What does that mean? That means that we have, for every liter, you have 0.25 moles of that compound. But we know that in solution, this compound does what? It breaks up into that plus two of these. Right? That's what it does in solution. Breaks up into the ions. Now, what's the concentration of calcium ions in that solution? It's a stoichiometry problem. If you got one of these, you only have one of those. So the calcium ions are the same concentration as the molecule, 0.25. How about chloride? Well, for chloride, for every one of these, you have 2 of those. So the concentration of chloride is 0.50 molar. Okay? How about the total? If you don't care about the individual ions, but you do want to know what's the total ionic concentration. Well, you've got 0.25 moles per liter of this one and 0.5 molars of that one per liter. So you have together 0.75 molar ions. Okay? There you go. I think I added this one on there. It's not on the slide. Yeah, that's not on the slide, but it's important, particularly if you're mixing up a solution that's going to be injected into a patient, you know, an IV. It's important that the concentration of dissolved components in that solution be the same as the concentration in the blood. Otherwise, you could injure or even kill your patient. All right. Which of the following solutions contains the greatest number of ions? Now, so there we have 3. Let's use Henry Ford. All right, we got A through D. See, am I still walk it over a little bit? There we go. A, B, C, and D. So A is 400 milliliters of 0.10 calcium chloride. 300 milliliters of 0.10, sodium chloride. This is calcium chloride. There we go. This is 200 milliliters. Let's see. Get all my zeros in there. Of 0.1 molar. Iron 3 chloride. And the last one, 800 milliliters of 0.10 molar sucrose. All right. Which has the greatest number of ions? Well, we can get rid of one of them right now. Sucrose doesn't make ions. Right? So now we only have to deal with 3 of them. Sodium chloride breaks apart into 2 ions for each molecule, 3 for calcium chloride, and 4 for iron 3 chloride. So if we want to know the number of ions, we need to know the number of molecules first. And moles is a perfectly legitimate unit of measure for numbers of things, right? So we don't have to calculate the actual numbers, like use 6.022 times 10 to the 23rd ions per mole. We're comparing them, find out the greatest number. So we really don't have to go that far. We just stop at moles. So if we have this molar solution, how many moles of sodium chloride do we have? Well, look at your formula. Molarity equals moles per volume. Solve it for moles. Molarity times volume equals the number of moles. So we use that relationship here. This molarity times the volume, right? 400 milliliters is 0.4 liters. Okay, let's do that for each one. So this one is 0.3 liters. This one is 0.2 liters. Right? So that gives us the number of formula units in moles. But we want to know total ions. So we need another conversion factor to convert from molecules. I shouldn't say that. That's not a molecule. A molecule stays together and never breaks apart. So we say formula units. Oops. Let's not write it that way. That can be viewed as something different. All right, for each formula unit, how many ions do you have, right? For this one, you have two ions. For this one, you have 3. And for this one, you have 4. Okay? Now we can do our calculations. We say 0.1 times 0.4 times 2. And that's 0.08. 0.08 moles. And that's ions. All right, 0.1 times 0.3 times 3 is 0.09 moles. And then the last one, 0.1 times 0.2 times 4 is 0.08. So that's the greatest number of ions from that solution. Right there. Pardon me. Yeah. Okay. So the moral of that story is there was no easy way to determine that answer. We could make it easier by using Henry Ford, do it the same way over and over and over again, and then compare the results. All right, let's see. Scoot that back a little bit. There we go. Okay. This kind of got the cart before the horse there. All right, the point is that the solution with the greatest number of ions is not necessarily the one with the highest concentration or the largest volume. You don't know that until you do the calculation. Okay. All right, what is a standard solution? A standard solution, by definition, is one in which the concentration is very accurately known. We can give you these hypotheticals and say you have so many moles per liter, and that's molarity. But actually preparing a standard solution is another issue, and it takes some care to do that. So I've got a little video that I'm going to call up here, and it takes a few minutes, but I think it's worth watching, and it may introduce terms or topics that we haven't covered yet, but it does focus on preparing a standard solution. All right, so here we go.
Hi, I'm Jared Hyman, an assistant professor of chemistry at Elon University. Today, I'll be taking you through the appropriate technique and procedure for preparing a chemical solution. One of the most important abilities at all levels of chemistry is the preparing of a solution of a specific concentration. First, we'll define some of the terms used in this process. A solution is a homogeneous mixture of two or more chemicals. For the simplest solution, a smaller amount of one chemical, called the solute, is placed in a larger amount of a second chemical, known as the solvent. Today, we will be preparing a solution of sodium chloride using a small amount of sodium chloride as our solute, added to a larger volume of water, our solvent. Before beginning any experiment, it's important to observe appropriate lab safety procedure and know the hazards of any chemicals you're working with. In any chemical reaction, it's important to keep track of the exact amount of reactants present, and for stoichiometric purposes, we use the term mole to define the amount of a substance. A mole is a counting term, similar to a dozen eggs, where 1 mole is equal to 6.022 times 10 to the 23rd things. As you can see, this is a really large number. The periodic table uses molar counting as a means of converting to a more experimental term of mass. For example, 1 mole of carbon atoms has a mass of 12.01 grams. In a compound such as sodium chloride, it's made up of 1 mole of sodium atoms with a mass of 22.98 grams per mole, along with 1 mole of chlorine atoms with a mass of 35.45 grams per mole, giving us a total of 58.43 grams per mole of sodium chloride. This means of using mass to determine the amount of a substance is useful for pure chemicals. But in the case of solutions, we now have a mixture of multiple different substances. Therefore, we express amount as a concentration. The most common unit for concentration in chemistry is molarity, abbreviated capital M, which indicates the number of moles of solute dissolved in a certain volume of the total solution. This gives molarity derived units of moles per liter. It is very important to note that this is a volume of solution, not the volume of solvent. Today, we will be preparing 500 milliliters of a 0.25 molar sodium chloride solution. Before beginning, it's important to map out your procedure for preparing this solution. Here, we'll look at the amount of sodium chloride we need in this solution. We know that we want to prepare a 0.25 molar solution, which means that there is 0.25 moles per liter of solution. We also know that we only want 500 milliliters of this solution, or a half liter. If we multiply these two terms together, we can see that we will need 0.125 moles of sodium chloride. From earlier, we can remember that there are 58.43 grams per mole of sodium chloride. We can determine that the exact mass that must be measured out is 7.304 grams of sodium chloride. In lab, obtain some sodium chloride in a clean lab scoop, and using a balance with some weighing paper, measure out as close to 7.304 grams as possible. marking down your exact mass. Note that if you go over the desired mass, it's never appropriate laboratory procedure to put the excess reagent back into the original container. Always use an additional container to collect the excess. Once you've measured out your solid and recorded the exact mass, transfer all of the solid to the appropriate sized volumetric flask. Volumetric flasks are made specifically for this purpose and should be used over other less accurate labware, such as beakers, Erlenmeyer flasks, or graduated cylinders. Here, we just transferred our solute to the 500 milliliter volumetric flask. If any solute remains on the weighing paper, use a spatula or a small amount of water to transfer the remaining salt. Next, add enough water so that the bulb area at the bottom of the flask is approximately half full. This will give you enough room to swirl the liquid, allowing the solute to completely dissolve. Again, it's critical that all of the solute is dissolved prior to filling to the appropriate volume, as different solutes may take up more volume in solution than their undissolved salts. Now that the sodium chloride is completely dissolved, we can fill the rest of the bulb area and some of the neck with water. You should now carefully and slowly add water, our solvent, as it begins to fill the neck. Once you approach the etched or printed line on the neck of the flask, you should add solvent dropwise, monitoring the location of the meniscus. Water, as a polar solvent, tends to cling to the glass walls of a flask. This phenomenon creates what is called a meniscus. The bottom of this curved meniscus should sit directly level with the line on the flask. At this point, there is exactly 500 milliliters of solution with an air of 0.2 milliliters. Different volume flasks have different air values. However, the air on a volumetric flask is much lower than any other type of glassware of similar volume. For example, the volume markings on a beaker or an Erlenmeyer flask are only accurate to plus or minus 5%, meaning if the meniscus were on the 500 milliliter line, it could be anywhere between 475 milliliters and 525 milliliters. On the other hand, using a volumetric flask, we know that the volume is exactly somewhere between 499.8 milliliters and 500.2 milliliters, meaning it's much more accurate. We now must determine the exact concentration of our solution by taking the mass that we measured out and dividing by formula mass for sodium chloride, 58.43 grams per mole, which gives us a total number of moles in our solution of 0.1253 moles. We can then take this number and divide by our value of 0.5000 liters to give us a total exact concentration of this solution of 0.2501 molar sodium chloride. This value and the contents of the solution should be clearly labeled on the chosen storage container for laboratory safety protocol. You now learn how to make a solution from a solid. Everything you need to do this demonstration in your lab is available from Carolina. We have experts who can assist you with any of your science demonstration needs. Visit us at carolinachemistry.com to see our complete line of products and kits for chemistry.
Okay. Let's see. Let me move to the next slide. Here we go. So, now you have in this example, a solution of sodium chloride in water, and you know the exact concentration, at least to 4 significant figures. Let's see, what else can we say? Just a couple of points. In the video, the demonstration was of adding the solid to the volumetric flask dry. There was no liquid in there to begin with. I like to start with a little bit of liquid. If it's a 500 milliliter flask, maybe put 100 milliliters in the bottom of it. which is just a matter of preference for most solutes. For some solutes, it's essential. For instance, if you're going to make up a solution of a strong base, derived from a strong base like sodium hydroxide pellets, or from a concentrated acid solution like sulfuric acid, and you're going to dissolve those in water, the reaction is extremely exothermic. In other words, it's hot enough if you have just a few milliliters of water in there and you add your solute, you can boil the water. And the hazard there, of course, is that if you have just a little bit of water and you boil it, it starts to spatter. And it spatters concentrated solution of the solute, which can be hazardous. So, especially for those situations that I know are going to be exothermic, I add a substantial amount of water to the flask before I add the solute. And that way, the temperature change is much less with a larger volume. That's for safety reasons, primarily. Okay, so if you weigh out your sample and you transfer it to the flask, all right, that's what was shown in the video. You don't add enough solvent to mark on the flask. Right. First, you add enough to dissolve the solute. And only then do you add enough solvent to reach the mark. And for those solutions that are extremely exothermic or endothermic, sometimes they get cold. What happens to a liquid? What happens to water when you heat it or cool it? It changes volume, doesn't it? So if you're going to prepare a solution at room temperature and it gets hot, you need to add enough water to bring it up into the neck and then let it cool before you finish diluting it. Vice versa. If it gets cold, let it come to room temperature and then add enough water to bring it to the mark. And you always look for that meniscus. Right? Aqueous solutions in glassware always form the concave meniscus. There are some liquids that form a convex meniscus. They're rare. The volumetric glassware that we're using here is calibrated for the concave meniscus. So when you reach the line here, like that, the glassware has been prepared to account for that type of meniscus. Okay. So then once you've got it to the mark, you cap it. Either you put a stopper in it that's designed to fit it, or if you don't have a stopper, or if it's not designed for a stopper, you get a piece of parafilm and wrap it over the top, seal it off good, and then you mix it. So what could possibly go wrong in mixing a solution like this? Well, you could make an error, weigh the sample incorrectly. Say that you put a piece of weighing paper or a plastic weigh boat on your balance and you don't zero it. Then you're not just weighing the contents that you add, but you're weighing the container too. So you think you're adding 10 grams of solute, but you're really only adding 8 grams, right? So there's a massive error possibility. You could lose some sample in transfer, right? When you pour it into the top of your flask, you could lose some of it, could spill out. Or if you don't wait long enough for your solute to go into solution, then you could you would have an error there. Or if you, here's an example, if you add enough solute, you want a particular concentration. So you weigh out the amount of solute, you add it to your flask, and you add water, and you stir it, you slosh it, but it all won't go into solution. Possibility that you want a concentration of solution that exceeds the solubility of the solute. In other words, you've already saturated the solution, and the rest of it won't go into solution. Right? So that's incomplete dissolution. So that's why very often, if I'm making a solution of a compound that I haven't done regularly, I go to the manual and I look it up and I say, what's the solubility of this solute? And I say, okay, I want this concentration. How does that compare to the solubility? If the concentration I want is less than the solubility, I'm good. If it exceeds it, then I need to do something else. Right? I got to go back to the drawing board. You may fill it up to the mark and either too little or too much, right? More often that you go too far, right? Why? Because if you squirt water down the neck of that flask right there, and you don't wait for it to drain down, then if you come up to the mark and then it's still draining, it's going to exceed the value. So that's an error with your volumetric measure. It's not the fault of the flask, it's the fault of the operator. I mentioned this one earlier. If the mixing is exothermic or endothermic, the volume will change. So you need to let it come to room temperature before you do the final dilution. If it's endothermic and the solution gets cold, it's going to shrink, correct? So if you have a cold solution and you fill it to the mark, what happens when it comes to room temperature? The volume increases, right? Now you got an error in volume that cannot be corrected. Well, can't be corrected easily. But if it's exothermic and you bring it to the mark, then what is it going to do when it cools? It shrinks, right? So in that case, it'll shrink, and once it's come to room temperature, you can bring it to the mark, right? So exothermic is not as much problem as endothermic. There are a number of other things that can go wrong, right? It's Murphy's Law in the lab. Anything that can go wrong probably will go wrong. So your best bet is to prepare in advance. That's why in my general chemistry classes where we have labs, I insist that my students come to lab prepared. In other words, they have their lab notebooks filled out with a procedure and several other things that I expect them to have in their lab notebooks before they walk in the class. Because your best guard against accidents is be prepared. Know what you're going to do before you walk in there. That's number one rule. Okay. So, suppose you are you use a solution of a definite concentration day in and day out. You have lots of samples to analyze, and you need a solution of a fixed concentration. But you don't have enough storage space to mix up 300 liters or 20 gallons of the solution that you're going to need over the next couple of weeks. what do? Well, the simplest thing to do is to make up a very concentrated solution of the solute. And then when you need to do your analysis, it's a simple matter of diluting a small amount of that concentrated down to the concentration of the working solution. So here's how that works. And it's a process we call dilution. And it's all based upon the fact that moles equals moles. Right? I'll show you what that means in just a second. Well, actually right now. So the moles of the solute that you extract from the concentrated container of solution is the same number of moles that you put in the dilution vessel and add more solvent. Okay? So here's what happens. Say you have a beaker and you've got a solution in here that's, say, 10 molar. Okay? Now you want to dilute that down to 0.1 molar. So you need a volumetric flask, right? You need an accurate volume to do this. So we've got this one already prepared. We know the solution is 10 molar. We've done the preparation before, just like was in the video. We made the solution, only we made it very concentrated. So now we have a volumetric flask. With a mark on it. And let's say we need, let's just keep it simple, 1 liter. So this is a 1 liter flask. Oh, by the way, did you notice in that video, there was a mention of volume in terms of milliliters, and it was written like this. Right? What's wrong with that picture? That is what I call an orphaned decimal. When you have a decimal on the left-hand side of your number, you better bracket it in with a 0, a placeholder. Otherwise, in a sentence, you could get that decimal confused with a period at the end of a sentence. So I hammer that on my students all the time. Say, I don't know where you learned to write decimals out, hanging out by themselves, but you need to unlearn it. Okay, back to our topic. So we've got a 1 liter flask. Now, we want to go from 10 molar to 0.1 molar. Right? If we take a volume out of here, right? We have a volume there. Can we calculate the number of moles? The answer is yes. All we need is the molarity times the volume equals a certain number of moles of solute that we've taken out. Okay? And we use volumetric glassware, usually a pipette, a device that is calibrated as accurately as this is to extract an exact volume. Now, we're going to put that number of moles in here, right? Call it N2. N1 and N2 are equal. The same number of moles that came out of here is going in that flask. All right? So now, we add enough solvent to the mark to make 1 liter. All right? Now we've taken the moles here and added solvent. So we've diluted that number of moles to that volume And what we want to do is to know what's the volume here that will give us that concentration. Okay? So over here, we've got this number of moles is equal to the new molarity times the new volume. Well, we know the new volume is 1 liter, and we know the molarity we want is 0.1 molar is equal to that number of moles. It's also equal to this number of moles, and we know the molarity here is 10. But we don't know how much to take out. So this expression is equal to that expression. And we only have to solve for that volume. So we say 10 molar times this volume equals 0.1 molar times this volume. And we solve for this one. Right? So we say 0.1 divided by 10 is 0.01 liters, which is 10 milliliters. And that's all we have to do. Take out 10 milliliters from here, put it in there, dilute it to 1 liter, and we have that concentration. That's the process of dilution, accurate dilution. I mean, not just dumping some water in there, which is dilution, but it's not accurate. Okay, and it's all based upon the fact that the number of moles you take out of here is the same number of moles you put in there. M1V1 equals M2V2. The reason for that is molarity times volume equals moles. So molarity times volume equals moles here. Molarity times volume equals moles there in the diluted solution. They're both equal to the same number, which means they're equal to each other. That's why this formula works. Another video.
Hi, I'm Jared Hyman, an assistant professor of chemistry at Elon University. Today I'll be taking you through the appropriate procedure and technique for diluting a solution. A common laboratory technique is preparing a more dilute solution from a concentrated stock solution. In this case, we are going to prepare a 0.250 liter solution of 0.01 molar. We know our stock solution has a concentration of 0.250 molar. The first thing we need to do is determine the exact number of moles in our dilute solution. We know our concentration needs to be 0.01 molar or 0.01 moles per liter. Since we know our number of moles per liter and we know the volume we need, we can calculate that we need exactly 0.0025 moles of sodium chloride. Knowing our stock solution contains 0.25 moles per liter, we can take the number of moles needed in our dilute solution and divide by the concentration of our stock solution to calculate the exact number of milliliters that must be transferred into our new solution. In this case, 0.01 liters of sodium chloride solution, or 10 milliliters. This is the stock solution of sodium chloride that we will be diluting. Make sure to pour the stock solution into another container before inserting the pipette into the solution. This is because you do not want to contaminate your stock solution. In this case, I'm using an Erlenmeyer flask. Notice that I have clearly labeled the flasks to adhere to proper laboratory safety protocol. To prepare our dilute solution, we will take a 10 milliliter aliquot of our stock solution using a 10 milliliter volumetric pipette. To use the pipette, place the pipette in the liquid to be collected. Squeeze the pipette bulb and allow the liquid to rise up the pipette. You should allow the liquid to pass the line marked on the pipette, but before the bulb. Remove the bulb and place your other thumb over the end, creating a seal, and slowly release just the corner of your thumb, allowing the liquid to exit so that the meniscus is directly on the line marked on the pipette. This takes some practice, and you may need to use the bulb to pull more liquid into the pipette again. Never pipette by mouth. Once you have the exact amount of liquid required in the pipette, hold your thumb firmly over the end and transfer the pipette to a new volumetric flask. In this case, a clean 250 milliliter volumetric flask. Allow all of the liquid to flow out of the pipette. Do not use the bulb to force the liquid out, as pipettes are designed to deliver the exact amount of liquid, and there may be a small amount of liquid remaining at the end. Remove the pipette and follow the same procedure as before, filling the volumetric flask with solvent, again monitoring the meniscus until the exact volume is reached. You've now learned how to prepare a dilute solution from a stock solution. To see how to prepare a stock solution, you can view our solution preparation video at carolina.com/video. Everything you need to perform this technique in your lab is available from Carolina. Visit us at carolinachemistry.com to see our complete line of products and kits for chemistry.
Okay. Now, what's wrong with that picture? Well, he did use a volumetric pipette, which is correct. He filled it up correctly. He let the volume in the pipette drop to the line and read the meniscus. The problem was, before you set the volume in the pipette, you should pull it out, take a Chem wipe, and just wipe down the outside of the pipette, because there is always something clinging to the outside, which you may introduce into your volumetric flask by accident. And that would bias, actually introduce an error. So you wipe down the outside, and then before you move it to your destination, you move your thumb and drop it to the line. Now, usually there will be something clinging to the end. You've already wiped off the outside, so you've got part of a drop clinging to the end. You just touch the inside of that pipette to the inside of the container, and it will remove that extra little drop on the end. Now you're ready to move it over to your volumetric flask, release your thumb, and let gravity do its thing. There will be a little bit left in the tip, always is. Those pipettes are calibrated to take into account that little extra that's left behind. But before you pull it out, once it's all drained down, touch the inside, the tip to the inside of your container, because there may be something clinging to the outside. The pipettes are calibrated for anything that stays on the inside of the pipette, but not on the outside. So that's how you deliver. And it does take practice. I mean, it's definitely an acquired skill. But it's a necessary skill if you're going to do any lab work using volumetric glassware. Nowadays, they have pipettes that are spring-loaded, and you can stick them in there, and they've got plastic tips, so there's no clinging to them. You can set it to pick up a certain amount and deliver it, and you can just do that over and over and over again. So if you're in a lab that requires transfer multiple times, then there are other ways to do it. But this is an extremely accurate way to prepare a working solution from a stock solution. All right, so this is just a follow-up to the video. And for your dilution, you follow the same procedure as making the stock solution. You taking all the precautions. All right, so let's work a problem. See if we understand the concepts. Say we have a 0.5 molar solution of sodium chloride. Okay, we're going to shift gears a little bit. You've got a 0.5 molar stock solution of sodium chloride sitting in a beaker. Okay. Which of the following would decrease the concentration of the salt solution? Which would make it less than 0.5, like down to 0.4, down to 0.3, so forth? Which one of these selections would accomplish that? Add water to the solution. Oh, definitely. If you add more solvent, you decrease the concentration of the salt. Pour some of the solution down the drain. Remember, concentration is an intensity factor. In other words, it doesn't matter how much you have, the concentration is still the same. Whether you have less amount, greater amount, as long as it's that concentration, that's constant, that stays that way, as long as you don't change anything else except to add or remove of that exact concentration. So pouring some of the solution down the drain won't do anything. It won't change it at all. No change. Add more sodium chloride. That will actually increase the concentration up to the point of saturation, of course. Past that, there won't be any change. So adding more sodium chloride will increase the concentration. And if it's 0.5 molar, you're a long way from saturated. Let the solution sit out on the open air for a couple of days. So what will happen? You get evaporation, correct? But you'll only evaporate the solvent, right? Sodium chloride won't evaporate, right? It's got a very high melting point and even higher vaporization point. So the sodium chloride will stay put, and you'll have the same amount in less volume, which means more concentration. Okay. Two of the above will decrease the concentration of the salt solution. No, just the one. Just A. Add water to the solution, that will decrease its concentration. All right. Now we're going to do a dilution. An accurate dilution. What's the minimum volume? Actually, it should actually just say, what is the exact volume of 2 molar sodium hydroxide solution that you need to make 150 milliliters of 0.8 molar sodium hydroxide solution? Okay. So we have our formula. M1V1 equals M2V2. Sometimes my students like to write MCVC for concentrated, and then MDVD for dilute. That's okay. It works. In fact, that may be preferable. Keep you from putting the numbers in the wrong place. So when you read a word problem like this, you know you're going to use that formula. Actually, for any word problem, I like to extract the information from the problem and put it on the board or put it on paper in a form that identifies what each one represents. Right? So you're starting off with a 2 molar sodium hydroxide solution. That's the concentrate. Okay. A minimum volume. So you need the volume of concentrated that needs to be extracted. That's unknown. And you want to make a 0.8 molar sodium hydroxide solution. So the dilute solution is going to be 0.8 molar. And you want a final volume of 150 milliliters. There we go. Now, when you do it that way, extracting this information from the word problem, it's more difficult to make a mistake putting these numbers in the wrong place. Because if you put these numbers in the wrong place up here, the formulas, I mean, garbage in, garbage out. You put the numbers in the wrong place, you're going to get the wrong answer. Right? So that's the main reason that I do it this way. Okay. Now, the other thing you need is the correct units. Right? Now, you're probably saying to yourself, that needs to be liters. And it can be. And then your answer will be in liters. But notice that this forms a ratio. If we solve for that one right here, then that one equals this one times that one divided by that one. Okay? Notice that molarity will cancel, right? Numerator, denominator. And then you'll be left with volume here. Well, that volume is ratioed to this volume, and the units of measure will automatically be the same. So when you have a ratio like this, you can leave that volume just like that and save yourself a step. Just recognizing that the answer will come out in those units. Okay? And the only reason you can do that is because this is a ratio. This is ratio to that, and that is ratio to that. So the units of measure don't matter. I mean, you don't have to change them to liters. So what we can do is say, this one, 0.8. I'm going to leave out the units just so I got more space. All right, that's crapping out on me. And then volume of diluted, 150. And then the molarity of the concentrated is 2 molar. Okay? So the answer, since these cancel one another, the answer is going to come out in milliliters. So 0.8 times 150 divided by 2 is 60. So the volume that you need is 60 milliliters, or 0.06 liters. If you had changed this to liters, that would come out in liters. Okay? The important thing to remember is you can leave the volume as is only for this type of formula. If you're actually going to calculate the molarity of a solution or use the original formula, the volume must be in liters. Okay, but for this one, it can be in any volume. Okay, let's see, we've got, am I getting close? Yeah, might be able to finish by noon. Okay, let's make room here. So, how do we solve stoichiometric problems involving solutions? Remember, when we did stoichiometry before, with a balanced equation, we had masses, right? Masses of reactants or masses of product, and we had to convert them to moles using molar mass. When we use solutions in a stoichiometric situation, we still need moles, but we don't use molar mass because we have a solution of a known concentration, and we have the formula that we can use to convert to moles, right? So we don't need molar mass, we need the concentration. So as always, write the compounds correctly, then balance the equation. Maybe you need to write the net ionic equation, but I'm not going to hammer that one. You can usually get by with the molecular formula. You need to know the moles, right? You can't go anywhere in a balanced equation without moles. You still need to determine which reactant is limiting, and that's the same procedure as always. Then you calculate the number of moles of reactant or product or whatever the case may be. So now we're using the same steps as before. The only difference is, in order to calculate moles, you use the concentration data to give you moles rather than molar mass to convert from mass to moles. We're going to work on an example. And then if you need to know grams or mass, then you can convert it from moles to mass. That's simple. All right, so here's an example. 10 milliliters of 0.3 molar sodium phosphate solution reacts with 20 milliliters of 0.2 molar lead 2 nitrate solution. Okay? So what do you get from that? Well, first of all, will a precipitate form, right? If a precipitate doesn't form, there's nothing to drive the reaction in this case. So will there be a precipitate forming? Well, let's write the formulas first. Right? We're going to have to do that anyway. Sodium phosphate. So we have sodium and phosphate. Sodium is like the potassium earlier. It's a 1+ charge, a 3- charge. You need 3 of them. Right? And this is in solution. And we're going to react that with lead 2 nitrate. So lead is a 2+ charge because the name says it is. And then nitrate is a 1- charge. So we need 2 nitrates. And this is aqueous solution. All right. Now, what's going to happen here? This is a double replacement reaction. You swap this anion for that anion, or that cation for that cation, whichever way works, and say, what does that give you? Well, sodium plus, nitrate minus. And we know that all sodium salts and all nitrate salts are soluble. So that's going to stay in solution, sodium nitrate. Okay. Lead 2 phosphate, how about that one? This is a 3-, this is a 2+. So how do you balance that? Cross multiply. So this is going to be a 3 over here, and this one is going to be a 2. Okay, so now we have a compound made. Let's see, we can remove these charges. Is that soluble? Well, you look it up in your table, right? Look it up in your, in the review document has a table. Let's see. Let's see, I don't have it with me. But you look it up. The cations across the top, the anions down the left-hand side, match them up. Lead 2 phosphate is insoluble. It forms a solid. Precipitates. Okay? So that answers the first question. What precipitate forms? Let's see. Why didn't it show me that before? Okay. Well, the first question is, what precipitate forms? We found that. Lead 2 phosphate. What other ions are there in the solution? Well, you've got 3 sodium ions floating around and 3 nitrate ions floating around. Plus, you may have some of these left over, right? Sodium ions, phosphate ions, lead ions, nitrate ions. They may still be in solution if one of them is in excess, correct? We may use one of them up, but then the other might be in excess. All right, so here's what we do. There's the information. 10 milliliters of 0.3 molar sodium phosphate. 10 milliliters of 0.3 molar. And 20 milliliters of 0.2 molar. Okay. Now, how many moles of this do we have to start with? Well, here's another trick I'm going to give you. Actually, let's do it kosher. 10 milliliters is how many liters? 3 places to the left, 0.10 liters. 0.01 liters times that number is what? 0.0030 moles. Okay, that's how many moles of sodium phosphate we have. How many moles of lead 2 nitrate do we have? Well, this is going to be 0.020 liters times this one, right? So that should be 0.0040 moles. Let me be sure I did that right. 0.02 times 0.2. Yeah, that's right. Okay. Now we know how many moles of each reactant we have. And remember, when you have a definite number of moles of each reactant, one of them is going to run out. So how do we determine which one runs out? Well, what did we forget to do? Balance the equation, right? Let's balance the equation. Okay, so we have a phosphate here and 2 there, so we need 2 here, right? That means 6 sodiums there, 6 nitrates, so we have 2 here, we need 3. 3 times 2 is 6, 3 leads, 3 leads, we're balanced. 2, 3, 6, 1 balances the equation. Now we can find the limiting reactant. So which one are we going to go for, right? Are we going to convert this number of moles to that? No. We convert it to the precipitate because that's what's driving the reaction. So we find out how many moles of this are produced. If 2 moles of this make 1 of those, then this would be half of that, 0.0015 moles of lead-3 phosphate. How about this one? This is 3 to 1, right? So for every 3 of these, there's 1 of those. So it would take 1/3 of that one. I can't do that in my head. 0.0013. 0.0013 moles of lead-2 phosphate. Right? So which one's limiting? This one produces the least amount. This one is limiting. Right there. That means this one is excess. So what does that actually mean? That means all of this is used up. Right? All of that lead is used up, but the nitrate ends up down here. So all of that lead is converted to this. Not all of the phosphate is converted. Right? It's excess. So there'll be some phosphate left over. All right, let's go back to the problem. What mass of precipitate will form? Well, we found out that this many moles will be produced. Right there. Now all we have to do is convert that to mass. So what's our conversion factor? Molar mass. What's the molar mass of lead-2 phosphate? Right, just have to add up the individuals. Right. So lead, how much does lead weigh? Lead is right here. Right. It's 207.2. 207.2 grams per mole, but we have 3 of them, right? And then we have 2 phosphoruses at 30.97. So 30.97, 2 times that, add it in. And then 2 times 4 is 8 oxygens, correct? So 16 times 8 is 811 and 54 grams per mole. Okay, that's a heavy compound. Now we multiply that times 0.0013. So I get 1.06 grams. Now, if I didn't make a mistake, okay, there we're calculating. Okay, I did make a mistake there. No, I didn't. 0.15. That's right. That's right. So there's the limiting reactant. Okay, we need to calculate, we need to figure how much lead, how much can be produced from that lead nitrate. There we go. 0.133. Okay, I should have carried it out another one, 33. So we're going to be off by a little bit, rounding error. So if we use this value here, right, instead of the one I used, and there's the molar mass, so 1.08 accounts for the rounding error. Okay. So with this same equation, what's the concentration of the nitrate ions that remain in solution after the reaction is complete. What happened to the nitrate ions? They were right here, weren't they? They ended up down here. So everything that we started with, we still have. So how many moles of nitrate are there? Well, you have 0.0040 moles of lead 2 nitrate. So what's the concentration of nitrate? For every one of these, you have 2 nitrates, right? So the nitrate concentration is going to be, well, it's going to be 0.0080 moles of nitrate. Well, what's the volume? The volume is the total, right? 0.01 plus 0.02 liters, 0.03 liters. And that'll give us the concentration of nitrate that is in solution. So I get 0.267. Nitrate. All right. Okay, we'll get there in a second. It's a spectator ion, right? Because it's the same on both sides of the arrow. 0.27. Rounded off. Okay. What's the concentration of phosphate that's left in solution after the reaction? Aha, this takes a little more thinking. All right, how much phosphate was actually used? We started off with how much? Well, 1 phosphate for every 1 sodium phosphate, right? So we started off with 0.0030 moles of phosphate. Right there. How much was actually used? Well, we have to go over here and say, this is how many moles would be produced of the phosphate, right? So how many moles of phosphate are produced on this side, which means they're used up? Well, for every one of these, you have 2 phosphates, right? So this is the 1 unit equivalent. Twice that much is phosphate. So 0.026, or actually 266. So we have 0.00266 moles of phosphate that were used. And this is how much you started with, 0.030. Right. So 4, 6 or 9 is 3. That's it. That's how many moles of phosphate you have left over. Now we just divide it by the total 0.03 liters. And that gives us our concentration of phosphate left in solution. Let's see, 0.00034 divided by 0.03 is 1.13 times 10 to the minus 2. Or if we move the decimal place over 2 places, it'd be like that, 0.0113. Okay. Right, so there you have 0.027. All right, they rounded off. I kept some decimals. That was used up, subtracted from 0.03, so 0.003. Okay, we're going to have a rounding error here. And they said 0.01 molar phosphate. I got 0.0113, but it's the same procedure. So that's what's left in solution of the phosphate. We didn't use it all up, right? Because that's excess. Okay. I think we're going to finish. I think this is the last topic of the day. Make some boardroom here. There we go. Now, excuse me. Neutralization reactions. Another type of reaction that involves solutions. It's very commonly done in chemistry, and well, it's called acid-base reaction. When you get an acid reacting with a base, they neutralize one another. But they only perfectly neutralize acid to base at the equivalence point, where the exact amount of, I'm going to use an example. Say we have hydrochloric acid reacting with sodium hydroxide. Okay? In this case, in solution, this is actually protons plus chloride plus sodium plus hydroxide. Okay? So the overall reaction is going to give us a salt in solution plus water. When we write it this way, see, this proton hydrogen ion combines with hydroxyls to give you water. And then you're still left with sodium and chloride ions in solution. So the net ionic equation for this reaction is this one plus this one yields this one. And these are the same on both sides. Right? So hydrogen ions plus hydroxyls yields water is the neutralization reaction. But we use the same steps as before. What we need to know is what's the concentration of hydrogen ions. I call them protons because that's what they are, right? A hydrogen ion is, a hydrogen atom is a proton and one electron, right? So if you strip the electron off, you've got a proton left. So the hydrogen ion plus the hydroxyl yields water. And what we need to know is what is the concentration of each. All right. And the steps are similar to the solution stoichiometry that we did before, only now we're using acid base. Right, so and when we have a known amount of, in this case, sulfuric acid, a known volume in a container, right? And we want to neutralize it in steps so that we know exactly how much base that we're adding. We use a burette. And this has the sodium hydroxide in it. And we add dropwise. Right, so we can control how much of the base we're adding. That's called a titration. So if we want to exactly react sodium hydroxide with sulfuric acid to produce sodium sulfate, that's 2, plus water, then we have a known volume of this one, and we add a certain volume of that one, but we know the concentration of this one exactly. Well, that's for titration. Let's get back to this problem because the data is a little bit different. So how many moles of sodium hydroxide are required to react with 1 liter of 0.5 molar sulfuric acid? 0.5 molar sulfuric acid, and there's 1 liter. All right? So, how many moles are required of this one? Well, we need a balanced equation, don't we? Okay. So we have 2 sodiums here, need 2 there, and then we have 2 hydroxyls and 2 hydrogens, which means 2 waters, actually. Because you only have 2 hydrogens here, but you have 2 there and 2 there. So we need 2 here. Okay. Now that should be balanced. 2 sodiums, 2 oxygens here in water, 2 oxygens. 2 hydrogens plus 2 hydrogens is 4 hydrogens, and then 1 sulfate. Right? We count sulfate as an independent balancing unit. So that equation is balanced. Now, how many moles of sodium hydroxide are required? Well, how many moles of sulfuric acid are there? 1 times 0.5 is 0.5 moles of sulfuric acid. But the ratio is for every one of these, there are 2 of these. So we actually need 1 mole of sodium hydroxide, right? Because of the stoichiometry. Okay, there you go. 1 mole of sodium hydroxide will exactly match. That is the stoichiometric amount of each one, the exact amount. All right. When we're talking about acids and bases, sometimes we want to use a different unit of measure. It's related to molarity, but it's special for acids and bases. And the reason for that is the ratio of acid and base changes with the stoichiometry. Like this acid produces 2 protons per mole of molecule, whereas this one only produces 1 hydroxyl to neutralize it. What if we could come up with a unit of measure that was based upon the number of hydrogens here and the number of hydroxyls there? Then it wouldn't matter what acid and what base it was. It would only matter that would be the only thing we're concerned with. So the name is normality, and what it refers to is the equivalent of acid or the equivalent of base per liter. Okay, so how many equivalents are there per molecule of sulfuric acid? For each molecule, there are 2 equivalents of hydrogens. So the molarity here leads to 1 normal. The normality is 1 equivalent per liter. When you have a half molar solution of sulfuric acid, it's actually 1 normal. For this one, you've got 1 mole per liter. So its molarity equals normality. Okay? Now we've got 1-to-1. A 1 normal solution of hydroxyl will exactly neutralize 1 normal solution of hydrogen ions if they're equal volumes. Okay? That's the advantage of using normality. Now it doesn't matter where they came from, acid or base. It really doesn't matter. This could be calcium hydroxide, which has 2 hydroxyls per molecule. And this could be phosphoric acid, which has 3 hydrogens per molecule. If this one's 1 normal and that one's 1 normal, it doesn't matter where they came from. Okay, that's the advantage of using normality. Now, how do we produce a 1 normal solution? Right? Well, in order to do that, you have to know that you have 1 mole of hydrogen ions per liter, or 1 equivalent, I should say, 1 equivalent of hydrogen ions per liter. In order to do that calculation, you need to know what the equivalent weight of sulfuric acid is. We know what the molar weight is, right? How many grams of H2SO4 will give you 1 mole of that compound, right? We just add it up, right? 2 hydrogens and 1 sulfur, 3207, and 4 oxygen, 64. So that's 98.09 grams per mole of compound. All right. If it takes that many grams to give you a mole of a compound, how many grams would it take to give you 1 equivalent? Or 1 mole of hydrogen ions? It only takes half that much, doesn't it? If that gives you 2, then half that much will give you 1. So the equivalent weight is half of that value, 49.05 grams per equivalent. Okay? I know this might spin your head around backwards, but believe me, once you get in the lab and start doing this stuff, this concept is extremely useful. All right. So this is just a picture showing you what I've explained to you. You can use it or not. So when you have an acid that produces 1 proton per molecule, the molar mass and the equivalent weight are exactly the same. So for hydrochloric acid and nitric acid, that's the same. For sulfuric acid, the equivalent weight is half, because for each mole of sulfuric acid, you produce 2 moles of hydrogen ions. Similarly, sodium hydroxide would be equivalent weight would be the same as molar mass, because it only has 1 hydroxyl per, and potassium hydroxide the same thing, 1 hydroxyl, and that's based upon this reaction, the net equation, right? Now it doesn't matter where it came from. If we know the normality, then it could be anything. Okay, so that's the definition of normality. The number of equivalents per liter. Right? And similarly, where we had molarity times volume equals moles equals number of moles. The molarity, the normality times volume equals the number of equivalents. Okay. I got 1 minute left, I think. No, actually, I've gone over. I was supposed to stop at 11:50, but we're almost finished, so I'm gonna. Yeah, this is the last concept. If you have barium hydroxide as your base, how many equivalents of barium hydroxide are there in 4 moles of barium hydroxide? Well, if you have 4 moles of the compound, you have twice as many hydroxyls, which means 8 moles or 8 equivalents. Okay, it's just that simple. And we're done. So on this Thursday, what I'll do, since Thursday is a built-in buffer day, I'll go into the homework on Cengage, and we'll work through some of those homework problems. And then the following Tuesday will be a review day, and we'll go through everything again and work out kinks, problems. And I'll use my review document that I generate for my CHEM100 class in seat. I use that document, and we'll run through some problems there. So we'll actually have 2 days of review, which I hope will help. So get into your homework. The review document is in Blackboard, right? So just go into Blackboard, and you'll find the review document. You'll find the key for it. You'll find worked problems for it, and work some of those problems and figure out where you're weakest. Concentrate on those. Bring those problems to class, and we'll solve them. Okay, so that's it. I'm done unless you have questions or comments.